going to review the definition of group homomorphism and some of its consequences that you'll prove on the adventure sheet on group homomorphisms. But I also want to compare them with the analogous statements for ring homomorphisms. So to get started, let's say that we have two groups, G where the operation is star and H where the operation is a smiley face. And let's say that we have phi, a homomorphism from G to H. So the definition of phi is, as a homomorphism, is that it's a map from G to H that preserves the algebraic structure. And so what do I mean by this? Here we're in groups land. What I mean by this is if I take two elements, G1 and G2 in G, and I apply the operation of the group G, and then I map using my homomorphism phi, the resulting map is going to allow me to take phi of G1 and phi of G2, and then I combine them using the operation of H. So what preserving the algebraic structure means is it means that if I do the operation and then apply the map, that's the same as applying the map and then doing the operation, but in the codomain group rather than in the domain group. Okay, and this is quite similar to what we saw as the definition of a ring homomorphism. However, we had more statements that we needed to make, and this is in part due to the fact that a ring has two operations and a group only has one. So let's say that A and B are rings. I'm not going to decipher the two different operations, though I will make a note about it. We'll say that phi is a map from a ring homomorphism from A to B, and we'll let A1 and A2 be elements of A. Okay, so then our definition of ring homomorphism, or preserving the ring structure, meant that if I take phi of A1 plus A2, this is the same as phi of A1 plus phi of A2. Now here the plus is in A, it's the addition operation for A, and here the plus is the addition operation for B. But we usually didn't use different notation for those operations. We just said, you have to know what ring this is in, and that's what I'm doing here. We also had that if I have phi A1 times A2, now here multiplication means within the ring A, that this is phi of A1 times in the ring B, this is multiplication in B times a phi of A2. But then we had a third property, which was that phi had to map the multiplicative identity for A to the multiplicative identity for B. We do not have, as part of the definition, this sort of property in group homomorphisms, but we do have as a consequence, and you'll prove this on your adventure sheet, that phi of the group identity for G in a group homomorphism maps to phi of the group, maps to the identity for H. However, this is not part of the definition, it's a consequence. You can prove it from the definition. Whereas for a ring, we had as a consequence, I use different phis. We had as a consequence phi 0a equals phi 0b. So it was a consequence that a ring homomorphism mapped the additive identity to the additive identity. It was part of the definition that it mapped the multiplicative identity to the multiplicative identity. Another consequence is about kernels. The kernel of a group homomorphism is the group identity if and only if phi is injective. This is a sort of statement that we saw with rings as well, that the kernel of phi is an identity. Which one? Maybe this is a discussion section question. Well, okay, it's probably not. It's the additive identity. The kernel of phi is the additive identity if and only if phi is injective. And this was also a statement that we had in linear algebra, that the kernel of a linear map is 0 if and only if the linear map is injective. Okay, so these are some consequences for us to explore in those cases. So we're now going to assume the same things that G and H are groups and A and B are rings, but we're going to add the assumption that phi in both situations is an isomorphism. Now, to check if phi is an isomorphism, you have to check two things. You have to check that it's a bijection, and you have to check that it's a homomorphism. So the definition in both cases is a bijective homomorphism. Maybe I should say bijective group homomorphism here, and bijective ring homomorphism here. Too often we forget to check one or the other of these statements when trying to show that two groups are isomorphic, but both are required. And intuitively, an isomorphism is just a relabeling of the group elements, but the relabeling, because it's a homomorphism, has to preserve the algebraic structure. And consequences of needing to preserve the algebraic structure are that if phi is an isomorphism, then phi preserves the order of the group and the order of any given element. And the analogs in ring homomorphisms are that ring homomorphisms have to preserve the number of elements in the ring. And the analog of the order of an element in a group is the characteristic of the ring. And by the way, I should highlight what I mean by preserves the order of the group. If phi is an isomorphism from G to H, phi is said to preserve the order of the group if G and H have the same order. Likewise, phi preserves the order of an element if I take an element of G and I map it under phi, it had the same order in G as phi of it had in G. So maybe I'll say what I mean by order of an element, at least, is that the order of a group means the order of the group G equals the order of H. The order of an element means the order of G1 equals the order of phi of G1 equals the order of G1. This is what preserving order means. Okay. It's also the case that A group isomorphism will preserve abelianness of the group. So what that means is that if phi is an isomorphism, which I'm assuming it is, that G is abelian if and only if H is abelian. An analogous statement in rings is that A is commutative if and only if B is commutative. But we had a few other types of objects that could occur with rings that couldn't occur with groups, and some of the analogous statements that applied to rings but not to groups were things like if A1 in A is a unit, implies that phi of A1, well, if and only if phi of A1 is a unit in B, or if I have A2 in A is a zero divisor, that meant that phi of A2 is a zero divisor in B. These sorts of statements have no analog in groups because there aren't analogs of units and zero divisors in groups because every element has an inverse. Okay, so those are the main facts that I wanted to summarize about group homomorphisms. The one remaining statement that I should make is highlighting the kernel. We see on our adventure sheet on groups that the kernel of a group homomorphism, I should have said this before talking about isomorphisms, of a homomorphism, is a subgroup, but the kernel of a ring homomorphism was not a subring, it was just an ideal. And so what this does is it draws a parallel not between subrings and subgroups, but between ideals and subgroups. And that's a statement that, although I should have said before I was talking about isomorphisms, I think is a really great statement to leave you with to ponder. Okay, thanks.